Here in Lesson 17, we'll talk about how probes are calibrated. I'm assuming that you're coming along in your lab work and you want your data to be more quantitative. The things we'll be talking about in this lesson are tip shape and size, the spring constant of the cantilever in the direction normal to the surface, perpendicular to the long axis of the cantilever along the length of the tip, and the deflection sensitivity, meaning you've got a voltage from the photodiode, the top quadrants minus the bottom quadrants, representing the up and down motion of the cantilever. And how do you turn that into a measure of deflection measured in nanometers? Remember that Hooke's law, the magnitude of the force is equal to that spring constant times the deflection. Before we get started, I just want to be clear about terms. If here in this sketch we have a cantilever chip sitting on a cantilever holder, I would call this thing, the whole thing, the probe assembly. And the constituent parts, I would call this a holder. That's what you actually stick into the AFM. Depending on your AFM, you might or might not have one. This part here that you grab with the tweezers, I call the cantilever chip, or the probe chip. Here, this is the cantilever, that's the beam. It's rectangular, sometimes triangular, and here is the tip. So when you refer to an AFM tip, that is just the end of the cantilever that is in contact with the sample, or coming close to the sample, and perhaps briefly touching it in a dynamic mode. Tips usually come in three shapes: cone, pyramid, or sphere. If you'd like to take a look at one, you would automatically think of microscopy. Well, they're too small for an optical microscope. With an optical microscope, you can see that one is there, but you can rarely make out any details unless the tip is unusually large. But you can turn to an electron microscope, provided that your tip and cantilever are sufficiently conductive. They have to be conductive because you're shooting a beam of electrons at it, and if they're insulators, the electrons just build up charge and then don't accept any more electrons in the electron beam to come and touch the sample. Unfortunately, that means that you would have to have access to an electron microscope, and you have to be good at handling the cantilever chips such that they don't end up at the bottom of that machine. So you would like to have a tip calibration function that you can do within the AFM. So one of the early ideas was plastic indentation, meaning that you take a soft, malleable sample, such as indium, and you purposefully push hard your tip into it, and then you come back and with a low force, you image the hole that you've left. Turns out that that's not used too often, because usually the cantilever is at a slight angle with respect to the sample, and this means as you indent, you also slide horizontally a little bit as the force becomes bigger. And this means that your hole is not a perfect hole, it's more like a streak. However, it's still a good option if your own AFM has a horizontal cantilever with a vertical tip. That's perfectly normal to the sample surface. You can also go over a sharp feature, a feature that is sharper than the tip on your cantilever. I gave a lesson on that called tip imaging. I believe it was lesson 5. And that sharp feature, it could be a spike. You can buy those delta function gratings, as I call them. You could use a sharp edge, or you could use a hole in the sample. So the presumption is you know the shape of that sharp feature, and that sharp feature is much smaller than your tip. And finally, there's something called tip reconstruction. That is when you image a sample, and in the software you take your image and apply a function that looks for the smallest radius of curvature in that image in all the different directions, and from that reconstructs what your tip must be like in order that your image come out the way that it does. Next we'll talk about the normal spring constant of the cantilever, which is associating with the flopping up and down of the cantilever in a direction nominally perpendicular to the sample surface, and not any slight twisting in this direction parallel to the sample surface. The cantilever is very stiff that way, and in any case we can't detect it with the detection system using bouncing a laser off the back of the cantilever. And we're not going to talk about the torsional spring constant due to lateral forces acting on the cantilever tip. Cantilevers come in 2 basic shapes, rectangles and triangles. Triangles were originally designed to counteract lateral forces, but it turns out that if you put your tip right at the very end of a triangle, it's more susceptible to lateral forces than if your tip is in the middle of a wide rectangle. If you want to stick with triangles, and you do want to be resistant to lateral forces, the tip should be located further back where the cross-sectional width is greater. That said, if you want to find the normal spring constant of your cantilever, back in the early days there were actually some calculations of that, and those were useful because based on the finite element analysis they were doing, they were able to say that by adding a reflective coating on the back of the cantilever, that increased the spring constant by up to 30%. But that's no longer really used because it's not a calibration in the sense of measuring something to determine your specific cantilever's spring constant. Another class of calibrations are loading calibrations, where you push the cantilever you're going to use in your experiment up against a known force or a known spring constant. And another cantilever, it could be a sensor, you could actually add little weights to it. That's very time consuming, of course. You can there are a variety of options that I would call geometric, which is you measure the width and length of your cantilever, and that you can do optically because the lengths certainly are big enough and the widths are generally big enough that you can see that in a calibrated optical microscope. And then you measure the resonant frequency and then calculates the spring constant. And then there's using the idea of thermal energy, and that is the following: 1/2 Boltzmann's constant times the temperature in Kelvin is equal to 1/2 the spring constant in the normal direction times the mean square deflection of the cantilever when it is unperturbed and vibrating due only to its thermal energy. Essentially, this equation says thermal energy equals potential energy of a spring. This approach is becoming more and more common because it's pretty easy to do, and more AFM manufacturers are including the software routine in their instruments. You do have to assume that your cantilever is driven only by thermal energy. That is, there are no vibration coming through to it, it's acoustically isolated, the laser that you're using to illuminate it and detect its position is not heating it up, etc. I'll also note that there are a couple of dozen, perhaps, methods of calibrating the torsional spring constant, but I think we'll save those for an advanced lesson someday. Deflection calibration. First of all, I assume you know how much your scanner moves. You can calibrate that by scanning over steps of known height or using interferometry. Then you put your tip in contact, firm contact, with a stiff sample, one stiff enough such that you can assume that it does not significantly deform as you apply a large force to it. You might start with the reflected light spot on the lower part of the photodiode, and as you apply a force by changing delta Z, that light spot will move up on the photodiode. This generates a change in photodiode voltage, delta VPD. We're looking for this calibration factor alpha, connecting it to the change in scanner height. So alpha is delta Z over delta VPD. Say that fast 5 times. It is typically about 100 nanometers per volt, but you must check that. You must check it every time you change a cantilever, or every time you change the position of the laser light on the cantilever. To find the deflection, then what you do while you are doing your experiment is you reposition the light spot in the center of the photodiode when the cantilever is free from influence of the sample. And your deflection is then your calibration factor times whatever voltage change during your experiment, right? Not during the calibration. If you're interested in the deflection of your cantilever when it's free or mostly free, that is slightly different from the situation that we just did, the supported situation, when the cantilever tip is in firm contact with the sample. In the free case, the angle at the end of the cantilever does not change quite so much as in the supported case. So now, for your deflection, what you do is you take the equation we just got and divided it by 1.09. 9% difference there. In summary for this lesson, I spoke about the 4 main ways of getting your tip's shape and size, the 4 main ways of getting your normal spring constant, and the one generally accepted way of converting from photodiode voltage to deflection. And remember, in order to have a quantitative magnitude of the force, you need to have both the cantilever spring constant and the deflection calibrated.